In this lesson, we're going to take a look at some long-term saving strategies. And I thought I'd start off by pointing out there's an old saying that goes, the best day to start saving for the future was the day you were born. The second best day is today. And I got to tell you, the older I get, the more I realize this statement has a lot of wisdom in it. So basically, we're going to just be modifying what we've already done with investments with compound interest. The one issue that we had with compound interest, whether you realized it or not, was that it was all about putting a certain amount of money in and investing it for a long period of time. And unlike most people, that doesn't work. So the reason it doesn't work is because very few people, like, let's just take you, for instance. How many of you just have $10,000 sitting around right now that you'd like to put in for your retirement? The answer is probably nobody. And if you do, I want to be friends with you. But seriously, what most people would do was put in a little bit of money on a regular basis. They wouldn't put big lump sum payments in. So usually what people will do is they'll set aside a certain amount of their paycheck. Maybe it's $25 or $100, whatever they can afford. And they'll just put that aside on a regular basis. So every week or every 2 weeks or every month or something like that. But they put in money regularly rather than put in one big lump sum payment. And that's what today's lesson's about. Now, before we get too far in, I'm going to warn you that the equation that we're going to see looks scary. It looks big and scary, but we already know what most of the variables in it are, and the rest are actually pretty straightforward. We're also not going to be rearranging this one. We're only going to be plugging it in and solving for the amount that we'll have later down the road, which means that we don't have to rearrange or solve the equation at all. We just have to plug in the numbers and evaluate it, which is helpful. So for our first example, we're going to start off with a relatively straightforward one where we're going to save $1,000 at the beginning of each year for 5 years so that we can take a trip 5 years from now. We're going to invest at a rate of 5% per year, compounded annually. How much will we have for our trip at the end of the 5 years? So there's two ways we can do this. Much like when we were doing or learning how to use compound interest, we saw that we could use simple interest and just take the money out and put it back in over and over again. And similarly, one way we could solve this is to just look at each of the payments separately and let them each build compound interest and then solve the compound interest equation 5 times. And that's basically what this picture does. So now it says that that first $1,000 is going to be invested for 5 years. And how much will it be worth in 5 years? The second $1,000 will be invested for 4 years. And then how much will it be worth? And then the third will be invested for 2 years. The third or for 3 years, the third for 2 years, the fourth for 1 year, and then on the 5th year, we're going to take the money out. So according to this, the future value of the annuity due. Now, don't get too caught up on those words. What we're going to consider here is something called an annuity. An annuity is just a fancy way of saying what we're doing here. So it's not a one-time investment. It's kind of a regular investment. And the future value is exactly what it sounds like. It's how much you'll have at the end of the investment in the future. It's a lot like the A. In fact, it basically is the same thing as the A we did in compound interest. It's just for these equations, we tend to use future value. That's what we call it. Okay, so according to this, our future value is going to be worth $5,801.92. So that's how much we'll have. Again, putting in $1,000 a year for 5 years. Now, I think you can see that that method maybe seems okay if we're doing 5 investments, one a year for 5 years. But what if we were doing it monthly for 20 years or weekly for 50 years? Then I think you can see that there'd be way too many of these equations to try and solve. So we actually do have a formula that we can use to solve it kind of in one step relatively easily. So that's going to be our method 2. And we're going to use this annuity equation, which is exactly what I was just talking about. It's to tell us how much we'll have in the future based on regular investments. So I'm just going to let you look at that equation for a moment and notice that there's a few variables in it. The I and the N are the interest rate per compound period or the number of compound periods. That's exactly the same as it was for compound interest. The two different variables, FV is the future value. It's how much we're going to have at the end of the investment. It's, again, a lot like our A value from compound interest. And the one really new variable is the C, and it's the cash payment invested per period. So basically, it's how much we're putting in regularly. So in the example we did here, we're putting in $1,000 each year, So C would be $1,000. It's just how much do we put in each time. Okay, so if we wanted to do it this way, we could solve it basically the same way we were solving the others, or setting it up the same way we set up the others. Let's list the things we know and the things we want. First of all, we want to know how much we're going to have in the future. So future value equals a question mark. The regular cash payment that we're going to be putting in is $1,000. The interest rate that we're given, going back up, is 5% per year compounded annually. So in this case, we can just write 5%. We don't have to convert it to another like per week or per month because it's already per year, and that's 0.05. And then our number of compounds, same thing. Because it's compounded annually for 5 years, we just have 5 compounds. Now that we have that, we just take our equation, future value equals our regular cash payment, 1 plus I to the exponent n minus 1 over I, 1 plus I. From here on in, the hardest part, honestly, is just making sure that we follow BEDMAS. So let's plug in the things that we know. We got 1,000, future value we don't know. On the top, we're going to have 1.05 to the exponent 5 minus 1 over 0.05, and then 1.05. Okay, so now BEDMAS says we should do the things within the brackets first. That last bracket, 1.05, there's nothing to do in it. It's already solved. It's 1.05. That middle square bracket we have to deal with. And what we're going to do is you're going to do the top of it and then divide by 0.05. So I'm going to do it in a couple extra steps than I normally would, but you can do it in a little bit shorter if you choose to. So I'm going to start by putting in 1.05 to the exponent 5. And I'm actually going to write out that number. It's 1.27628. And again, I don't want to round off too much here because any rounding could cause a little bit of a problem down the road. Okay, so all I've done so far is the 1.05 to the exponent 5. Now I'm going to subtract the 1. So when I subtract 1 from to 1.27, I get 0.27628 over 0.05 times 1.05. And finally, I'm going to do the 0.27628 divided by 0.05. And that gives me 1,000 times 5.5256. I think that's probably enough decimals. And then multiply that by 1.05. So I have that 5.5256 in my calculator, so I'm just going to multiply it by 1,000 and then multiply it by 1.05. And my answer is, I'm running out of room here, but 5,801.91 cents. Now, if I just compare it to the answer we got up here, doing it the long way, you'll see that I got the same number. I'm 1 cent off. That's sheerly rounding error. But even then, keeping all the digits that I did keep still gave a slight rounding error. So keeping very few digits is going to create a fairly significant rounding error to the point where our final answer could be off by hundreds of dollars. And if you're off by hundreds of dollars when you're only making $800 of interest, you're not really doing a calculation anymore. You're just guessing. So please make sure that you are keeping some significant digits there. Okay, so just to recap what we did there, we took our equation. We didn't have to rearrange it or anything. We listed our variables, the knowns and unknowns, the same way we did for compound interest and simple interest. And then we just plugged them into our formula and used BEDMAS to solve it. That's it. So let's try that again using a few more examples. Okay, example 1. On the day their daughter was born, Al and Amrita invested $1,000 for her education. Rivit, which is the daughter, just turned 18. The interest earned was compounded monthly, and the investment earned 6% interest per year. Now notice that this is not actually an annuity equation like the one we just solved. This is telling us that we're putting in $1,000 once and letting it sit. That's just regular compound interest. So for part A, to solve this equation, we'll need to use the compound interest equation from the previous lesson, or I shouldn't say the previous lesson, but a previous lesson, since that was a little while ago. A equals P times 1 plus I to the exponent n. Summarize all of the variables that are known for this question. Okay, so A is the thing we're looking for. P is the principal as starting amount, that's the 1,000. I is the interest rate in this case, since we're compounding monthly, the interest rate per month. Now we have the interest rate per year, so what we have to do is take that 6% and divide it by 12, since there are 12 months in a year. When we do that, we get 0.5%, which actually simplifies down to 0.005. And then n is our number of compound periods. It's how many times we compound. And that happens 12 times a year. For 18 years, for a total of 216 compounds. That's a lot of compounds. Part B, how much will the $1,000 investment be worth on Rivit's 18th birthday? Well, we just take our equation, A equals P 1 plus I to the exponent n, and plug in some numbers. So P is 1,000. Usually I just do this in one step because it's pretty easy. 1 plus 0.005 is 1.005 to the exponent 216. So remember BEDMAS, we have to do the exponent before we multiply by the 1,000. So 1.005 to the exponent 216 gives us something a little less than 3. Multiply that by 1,000, and we get $2,936.77 when we round off. Okay, so the $1,000 investment over 18 years became almost $3,000. For part C, how much interest would, I guess I would say, would she have earned if the savings account had only paid 0.03% per year? So if, let me just put that in there, that's grammatically bothering me. If she left her money in a savings account instead of putting it into a GIC or some kind of better investment, she would have gotten a lot less interest. Now let's see what difference that would have made on how much money she'd have when she turns 18. So we're going to just list the variables again quickly. These are pretty quick because they're pretty much the same except for the interest rate. The interest rate now is 0.3% a year divided by 12. 0.3 divided by 12 is 0.025%. And then we get rid of that percent and it becomes 0.00025. And n is still monthly for 18 years, so that's still 216. So only one variable changed. I'm not going to write the equation out again. We have it right above us, and we're plugging in at just one different number. So this is going to be, it's going to be 1,000 times 1.00025 to the exponent 216. So I'll take 1.00025 to the exponent 216, multiply that by 1,000, and we get $1,055.48. And I got to point out the question actually asks us to find how much interest she made. I was a little bit fake there when I said A equals. It's actually I that we want. But the good news is we know that the amount of interest is just going to be the amount that we have at the end minus the amount that we put at the beginning. So 1,055.48 minus 1,000 is $55.48. So just to compare that, if she left the money, or if they just put the money into the savings account for 18 years, the interest on it would have been about $55. If they put the money into a GIC at 6% a year, which is not unreasonable, they would have made almost $2,000 in interest. $2,000 in interest versus $55 in interest. I'd say that's a pretty significant difference. Okay, let's continue on. Let's continue on with D. Based on your answers from B and C, how important is interest on the future value? And the answer is very. So we just saw that it did make a huge difference. Okay, now we'll go on to question 2. Okay, so Rivit is 18 now, and she gets a part-time job after high school, decides to save $20 per week into an investment that pays 5.2% per year compounded weekly. She continues these investments from her 18th birthday until she is 28. Okay, so now I'm looking at this question, and it's a little different than question 1 because we're not talking about a one-time investment. We're talking about investing $20 per week. And as soon as we're talking about per week, that's an annuity equation. So let's just answer these couple of questions, and then we'll actually get to the annuity equation itself. Part A is how many payments would she have made in total? So how many payments of $20 did she put in? And she put in weekly for 10 years. So 10 times 52 is 520 payments. So she made 520 investments. And again, if we went back and used compound interest, we could solve it without the annuity equation, but we'd have to do compound interest equation 520 times, which seems a little tedious. So let's use the new version. For part B, what would her savings have been worth if she didn't get any interest at all? So this is the example of the person who puts $20 in the jar on their desk every week, which people do. So if she doesn't get any interest at all, she'll get $20 times 520 investments. And 20 times 520 is, $10,400. Well, that's not too bad. $10,400 is nothing to laugh at. That's enough to buy a car, a used cheap car, but a car. If we go to part C, let's figure out how much she'd have if she actually invested it at the 5.2% per year compounded weekly. Okay, so we'll start off by listing the things we know and the things we want. We want the future value. We know that her regular investment, her regular cash investment is $20. We know that the interest rate is 5.2% per year, but we have to divide that by 52 because we want percent per week. So 5.2 divided by 52 gives us 0.1%, which is the same thing as 0.001. And then the number of actual payments, or the number of compounds, is actually the same as the number of payments. It's going to be 520, since it's basically how many weeks are there in 10 years. Okay, so now let's plug those into our equation. Future value equals 20, 1.001 to the exponent 520 minus 1 over 0.001 times 1.001. Okay, now just to save a little bit of time and energy, I think I'm going to try and do that entire big bracket as one thing. So we'll follow BEDMAS here. Make sure that that is clear, that that -1 is over the fraction. So I'm going to type in 1.001 to the exponent 520. And I get about 1.68. I'm now going to subtract the 1, and that means the top of the fraction will be 0.68. And finally, I'm going to divide by 0.001 and get 681.59 something. And notice this isn't actually a dollar value yet, so I should keep maybe a couple of extra decimals. 59067. And then we'll multiply that by 20 and multiply that by 1.001. And now we should get dollars out. Okay, so final answer, $13,645.45. Okay, so basically, if she put $20 a week in a jar, she would get $10,400. And by putting it into a fairly reasonable investment, she's getting out $13,645. So an extra $3,200 in interest. That's not too bad. That's almost a third of her original investment. So I don't know about you, but I could always use an extra $3,200. So consider looking at investments rather than just shoving money in jars. Is essentially the message of this question. All right, one more to finish things off. Gavin is 15, which is probably most of you are 15, 16, 17, 18, somewhere in that ballpark. So this is about your age, and works after high school washing dishes in a restaurant. He has decided to invest $200 per month. That's not unreasonable. He is investing in a fund that pays 6% interest rate, which with the interest compounded monthly. Okay, so now I am going to tell you one thing about this equation that I haven't mentioned so far, and we're not going to worry about it. It's a detail we don't need to consider. And that's that the equation only works if the money is compounded at the same rate that the payments are put in. So this works because it's compounded monthly and putting in 200 a month. If we compounded weekly, we'd put in money per week and so on. There is a way to modify that, but it's a little bit beyond what we want to do in this course. So we'll just do questions where the compound period and the rate at which the money's being put in are the same. Okay, so let's just talk about what Gavin has here. So he's putting money in for 5 years essentially, until he's 20 years old. So we don't know what future value is going to be. That's what we're trying to find. We know that the regular cash payments, how much he's putting in, is 200 each month. We need the interest rate per month, and we're told that it's 6% per year. We'll divide that by 12. So 6% divided by 12 is 0.5%, and 0.5% is 0.005. And in this case, the number of compound periods is just going to be 5 years at 1 per month. So 12 times 5 is 60 payments. Now that we have that, let's just plug it into the equation. So we have 1.005 to the exponent 60 minus 1 over 0.005. Oh, little screen flash there. Okay, it seems to be working now, so let's keep going. And then we do 1.005 at the end there. Now, same thing, rather than write this out as 3 or 4 or 5 lines, let's just try and do this in our calculators. So 1.005 to the exponent 60 gives us about 1.348. Subtract 1 from that, and then divide that by 0.005. And we should get out 20 times 69.77003051. Again, keeping a few extra decimal places there so that we're as accurate as possible. And now that we have that number, multiply it by 20 and multiply that by 1.005. And we get $1,402.38. Okay, that definitely does not look right. Oh, and a quick observation tells me why. So I put $20 instead of 200 a month. So let's add a 0 there, a 0 there, and that's going to add one more 0 here. So $14,023 and I think 78 cents. If we go back to the number that was still in my calculator. Okay, so a good indicator, look at your numbers and see if they make sense. I was thinking if you put in 200 a month for 5 years, it'd be more than 14. That's only 7 months of payments. That's not even interest included. So it had to be more than that. Okay, The next couple we're going to do pretty quickly because they're basically just verification or modifications of this one. And again, it's just to show you what happens in the long term. So that was how much Gavin would have if he saved $200 a month for 5 years from 15 to 20. Now what we're going to do is save it all the way until he's 35, starting at age 15. So the only thing that's really going to change here, the future value is still unknown. He's still putting in 200 a month. He's still investing at the same interest rate. The only thing that's going to change is the number of payments, which in this case is also the number of compound periods. So now he's doing it for 20 years at 12 times a year, or 240 payments. So now we just set up basically the same equation that we have above, just with an exponent of 240. So 1.005 to the exponent 240, subtract 1, divide by 0.005, multiply by 200, multiply by 1.005. And that would be $92,870.22. Okay, so this might be at the age where Gavin's looking to buy a house. And I would say having an extra $92,000, $93,000 to put towards it might be a little bit helpful. What about if Gavin lets the money continue to build until he's age 65? So now we're starting to look at a retirement. So same idea, future value. I don't even know why we're listing all these. They're the same as they were before. Again, the only thing that changes is the number of compound periods or the number of payments. So if he's going from 15 to 65, that's 50 years at 12 payments per year. And 50 times 12 is 600. So 200 times 1.005 to the 600 minus 1 divided by 0.05 times 1.005. So I'm going to punch that into my calculator as 1.005 to the exponent 600. It gives me a number almost 20. Subtract 1 gives me like 18.9. Divide by 0.005. It gives me 3787. Multiply that by 200. Multiply that by 1.005. And the grand total is $761,225.41. So $750,000 for retirement. That's enough to buy something nice, something fairly nice. Okay, now one final little thing that we want to do just to kind of compare again is we're going to also do age 65, but in this time, instead of 6% interest a year, let's say that we could get him an investment of 8.4% per year. So now this is going to be the exact same as the question above in C. The only difference is the interest rate is changed. So we'll do 8.4% divided by 12 because we need percentage per month. 8.4% divided by 12 is 0.7% divided by 100 to convert it to a decimal, and it's 0.007. So basically we're doing the equation above. We're just replacing the 0.005s with 0.007s. Doesn't seem like a big difference. Let's see if it does much. So 1.007 to the 600 minus 1 over 0.007 times 1.007. Okay, 1.007 to the exponent 600. 1.007 to the exponent 600 gives me 65.7. subtract 1 gives me 64.7. Divide by 0.007 gives me 9,245-ish. And then multiply that by 200 and multiply that by 1.007. And that gives me, oh my, $1,862,020.58. So if we compare those, just going from an investment that paid 6% interest to an investment that paid 8.4% interest took us from having $750,000 to having almost $2 million. That is a pretty significant jump. It's about 2.5 times as much money. That's huge. So one of the reasons I pointed this out is because if you do investments at some point, one thing that they often do is investment companies will tell you, oh yeah, it pays like 3% interest a year, but we take a 0.5% cut. It doesn't sound like a lot, but if they're taking away from your interest rate, it could make a huge difference in the long run. Now that said, if you're investing with a company who gets you better interest rates, even taking the 0.5 doesn't make a big difference. So I know that, for instance, our pension plan invests a huge amount of money, and a lot of people have complained because the person who's in charge of the pension plan, the absolute boss who's in charge of investing for us, he makes a couple $1,000,000 a year, which is a lot of money. It seems like a lot of pay, but at the same time, when we have a huge investment, if he can get 0.1% better interest rates than the next guy, he's basically working for less than nothing. He's paying off in the long run quite a bit. So it's well worth it to get that little bit of extra percentage, but don't sacrifice. Don't basically go with a lousy broker because they take a lower percentage cut if they end up offering a lower percentage to begin with. Anyway, this has been a pretty taxing lesson, no pun intended there. It's been a fairly long lesson with a big equation, so I don't want to go too much further. There's just a couple of practice problems, and they're basically going to just make sure that you understand how to use the equation that you just learned. And much like the others, I've given approximate answers here. If you're way off, chances are you've made a mistake. You've multiplied when you were supposed to divide or did BEDMAS wrong or something like that. If your numbers are anywhere close to the answers that I've given down there, they're likely correct. But because a small change can cause rounding error, I don't want to put down exact answers. All right, if you need help with these, let me know. Otherwise, good luck.